In this lecture, we'll be looking at probabilistic models and how to define them. Now, a probabilistic model is just a model of a random process or of an experiment where we want to know what the possible outcomes are. So the first step in defining that probabilistic model is to define those possible outcomes. For instance, if we're flipping a coin, that would be heads or tails. Those are our possible outcomes. If we're rolling a die, there's 6 possible outcomes. 1, 2, 3, 4, 5, or 6. Now, the second piece of this is to define the beliefs about the likelihood of each of those outcomes. And that ultimately becomes a percentage chance, an opportunity for each of those outcomes to occur. Now, circling back to the first step a little bit, we want to talk about that list of possible outcomes, all the different things that it could be. Now, in probability, that list of possible outcomes is more formally known as a set. And a set also is known as a sample space. All 3 of those words really are kind of interchangeable in the world of probability. So when we talk about a sample space is just the collection or the set of all possible outcomes of our experiment. Now, sets are denoted in probabilistic systems by a capital omega. And anytime you see that capital omega, it is the sample space. It is the collection of all possible outcomes for that experiment. Now, elements within a set ultimately have to have some very finite rules. The first one is that they have to be mutually exclusive. Any outcome of the experiment should not be possible if a different outcome happened. In other words, only one outcome of that experiment can happen at a time. The second element of a set is that it must be collectively exhaustive. Now, collectively exhaustive is just a fancy way of saying that at the end of the day, all of the different outcomes have to be listed. For instance, if I have a set that is for a die, and its options are 1, 2, 3, 4, 5, and 6, but I don't include 5, then that set is no longer collectively exhaustive. Even if I have 1, 2, 3, 4, and 6, because 5 is not there, it's not collectively exhaustive. Finally, elements of a set have to be sufficiently precise. Now, we'll come back to that one because it is a little bit more complicated, but it ultimately is up to you as the designer of the experiments to decide what is sufficiently precise. Now, at the end of the day, the goal of defining your set is that the set should be one where you can point at a specific element of that set and say, that is the one and the only one that occurred as a result of this system. Physically different outcomes should be distinguished in sample space. They should be different from each other. And they should also correspond to distinct points. But when we say physically different outcomes, what do we really mean? What that means is they should be different in relevant aspects, but not necessarily in irrelevant aspects. Now, before we dig into that, let's spend a little bit of time and look at an example of what a set is. In the world of a set or of a sample space, which you'll notice is indicated here by our capital omega, we divide our sample space into any set of possible options. If we go back to our coin flip, that we have a heads and a tails, and those are both valid options within our sample space. Now, another option, as we mentioned earlier, might be that rolling of a die, in which case you have a 1, a 2, a 3, 4, 5, and 6. Now, all of those are different points within our sample space, and when we look at these, they are, for a die roll, mutually exclusive and collectively exhaustive. Now, if we take a look at a different example here, let's go back to our coin flip for a second. In the basic case, we have heads and tails. And those are the only two elements in our sample space. But let's say that we want to take this a little bit further. Let's say that we happen to look out the window and see if it's raining. And so in reality, we say, oh, well, maybe there's actually 4 different options. That it's heads and it's raining. That it's heads and it's not raining. That it's tails and it's raining. And that it's tails and it's not raining. Now, you may look at that and say, what does raining have to do with whether a coin lands heads or tails if you're inside? And the answer is probably nothing. So going back to our sufficiently precise, this is an example of something that is overly precise, where we have irrelevant information in whether it's raining or not raining. Now, maybe the point of your experiment is to decide if raining has an impact on whether a coin lands heads or tails, in which case this information is probably important because without it, you wouldn't be able to reach a decision. But in most cases, this information would be irrelevant. We can say that by being inside that the rain does not have an impact on our experiment. And so being able to understand what elements within a sample space are relevant and irrelevant in the way you define those elements ultimately has an impact on what your probability is. In any case, exactly one outcome will always be true, and only one outcome can be true. Whenever you put together a model, it's up to you to decide how detailed that model needs to be. And the right level of detail in that model is one that captures the information that you, as the person designing the experiment, decides needs to be there.